There we go. All right. So we're starting with number 9, folks. We've got a train car moving at some speed, so it has momentum, collides and connects with a train car of equal mass. Ooh, perfectly inelastic collision. Multiples become 1. Moving in the same direction with this. What is the speed of the connected cars? How much KE the system decreased during the collision? All right. So, start off with the text part of my Y. This is a totally inelastic collision. So, momentum is conserved, but not kinetic energy. The cars together will move slower than the faster car by itself, but faster than the slower car. And I think also there will be less KE in the system after the collision than before. Yeah, that seems like all the salient understandings I want to show. Yeah. Questions are good? So let's do some diagrams. Now, how do they label them? I'm just going to call them A and B. We'll call this one A, we'll call this one B, and this will be AB. So we have momentum of A beforehand, momentum of B beforehand, and then the momentum of this new object AB. Okay? And if I drew them correctly, the momentum of A and the momentum of B arrows would add up to be the momentum of the AB arrow. Because momentum's conserved. Yeah, let me drop those into my document and then starting on some math. If you have questions, just give me a yell. Glad to take them. All right, let's see. From my equation sheet, I know that momentum of the system beforehand equals the momentum of the system afterwards. That's mathematically how we say conservation of momentum. I know momentum is mass times velocity, and kinetic energy is 1/2 the inertia speed squared. Good? That's just from our equation. So, beforehand, I have momentum of A plus momentum of B, and that's going to equal the momentum of AB. I'll worry about the kinetic energy afterwards, because they want to know the velocity of them together and then the kinetic energy afterwards. So this would be mass of A, velocity of A, plus mass of B, velocity of B, equals the mass of them combined, which would be the mass of A plus the mass of B, and then their combined, that new object is object AB. Now nicely, I've predicted all the velocities going in the same direction. Is it okay if we call that direction positive? Yeah, because negative signs are a pain to deal with. And now, ooh, they told me they had the same mass, right? So I think I'll simplify here and just do mass of VA plus mass and then VB equals 2m VAB. And I dropped my vector symbols because we said they're all positive. I can simplify, can't I? Yeah. All my masses go away. So 2.5 and 1. I can do that in my head. Almost. Right? Now, any question on that, or should we jump right to kinetic energy? Right ahead, jump right ahead. Yeah. So I want the change in my kinetic energy, right? Or do they? Let's see. What did they actually ask for? Decrease during the collision. So I'm going to give them a positive value, but I'm probably going to come up with a negative. I'll come up with a negative value, but I'll put in the positive one into the site because they're saying decrease. So I'm expecting it to get smaller. So that would be KE final minus KE initial, right? Because change is always final minus initial. Feedback kinetic energy. The final is going to be the kinetic energy of object AB. The initial, bless you, would be the kinetic energy of A plus the kinetic energy of B. One half mass of AB, speed of AB squared minus 1/2 mass of A, speed of A squared plus 1/2 mass of B, speed of v squared. Now, because I'm looking for the value on the left, I can't cancel anything out. I could combine some things to make my algebra easier, right? Or make it less numbers to put in the calculator. So I could say, oh, well, every term has a half. Let me pull that out. If I replace this with 2m, and this with m, and that with m, then I could pull an m out. And I'd be left up here with 2 VAB squared minus VA squared plus VB squared. Right? And then I can substitute in. So, yes, did I make an algebra mistake? No, I'm wrong. So I pulled a half m from each term. All right, so I'll put in my values. Let's see, 1/2, and my mass was 25,000. To 1.75 minus 2.5 squared plus 1.00. Oh, that's kind of nasty, though. But at least it's all numbers, right? As long as I don't mess up my order of operations, I think I'll be okay. I got a negative number. That's good. -1. Oops. Said 1, I wrote 4. 1, 4, 0, 6, 2.5 joules. So the answer I'm going to actually put in, though, is going to be 1, 4, how many sig figs? 3? 1, 0, 0 joules. Because they asked me how much it went down. So I'm thinking they want the positive value there. Let me check and see. That's right. 1.75. Nice. I love how it turns slightly green first. Is that right? Yay! All right, so we're doing number 3 here. We have this giant egg, firework that explodes. So let's see, we know that momentum is conserved. So the same before and after the explosion for the system. Does that mean it's the same for each piece before and after? Not necessarily, right? because how about momentum can change for the parts, but not the whole thing. And also I would put in there momentum is a vector, so direction is important. Cool. Alright, now I need to do a diagram. So there's my before diagram, right? Momentum is 0. Afterwards, which one do they call A? Which one do they call A?
Wait, can we just draw literally after? Or the part like that?
Because the setup in the rubric has before and after. Oh, this is like the reverse of what we just did. Kind of, right? So maybe with some more zeros. I think that finishes off my Y. Let me grab those. Now remember, don't be intimidated by my artistic ability here, folks. Ooh, that's weird.
Mr. Kaufman?
Yeah.
Is kinetic energy conserved in an elastic collision?
It is.
Oh, okay.
All right. So that's my Y. Any questions, disagreements, agreements? So let's look at the problem. So what is the magnitude of the momentum of piece A before the explosion? Oh, that's got to be 0. Because it's not moving. It's at rest. During the explosion, what is the magnitude of force on piece A and piece B greater than or equal to? Oh, wait a minute. Force equal to. Yay. Okay, so the component of the momentum of piece B is measured at positive 500 kilogram meters per second after the explosion. Find the component of the momentum of piece A after the explosion. Okay. So, momentum of the system has to equal momentum of the system, right? Momentum of AB must equal momentum of A plus momentum of B. They told us tell this direction positive. Is everyone okay with that? Yeah? That would make the other direction negative. So I'm going to write, I wrote this as vectors, and that's correct as vectors. I'm going to put in my directionality to make life better. Alright? Or, well, I know, I'm going to put in my values. I know momentum of AB is 0, because it's at rest. Momentum of A, I don't know. Still a vector. Plus, momentum of B is plus 500 kilogram meters per second. I do some tricky math, and I get negative 500 kilogram meters per second. And I'm done. Now I just check it. Then I go home happy. All right. So on to number 5. Oh, we've got another perfectly inelastic collision, right? And they are asking us about the kinetic energy of the system. All right. Well, let's see. So, in the totally inelastic collision, momentum will be conserved, but kinetic energy will be less after the collision. The carts will be moving slower after the collision than before. I should probably have zoomed in on it. Yeah, I think that about covers it, right? We're going to slow down. So, this friction's Amtrak, identical car again. A, B, momentum of A, momentum of B equals 0. Momentum of AB. Yay?
Yay.
Remember, don't be intimidated by my artistic ability. You too can learn how to draw this well. Maybe one day. Lots of practice.
No, that does not equal that. Hold on. Wait a second.
Oh, did I put in there? I think the kinetic energy will be less. Yes, good. Here. So, momentum of the system equals momentum afterwards of the system. Momentum equals mv. They both have the same mass, right?
Yes.
Alright, so I'm just going to use M for mass rather than MA and MB, right? So M VA plus 0 equals 2M, because it's twice the mass, VAB. So VA equals 2 VAB. .45. So 0.45 meters per second equals 2 VAB. Excuse me, VAB equals 0. 0.225 meters per second. Now I'm not going to box that because that's not actually an answer they asked for. But I know I need it. Because what they want to know is the kinetic energy before versus the kinetic energy after, right? And that's the two things they want. Initial kinetic energy of the system and final of the system. So, KE initial would equal the KE of A, whoops, I forget that. A plus the KE of B. So 1/2 mv speed of A squared, 1/2 m speed of B squared. Oh, that's 0. Wait, nope. And my KE after would be the KE of object AB, 1/2 2m VAB speed squared, so 1/2 times 2 times 0.12 kilograms times 0.225 meters per second.